Okay, in this example, we have a fence that is 30 feet tall and it runs parallel to a tall building that has a distance that is 6 feet from the fence. So this is the fence here that I just highlighted in pink. Here's the building, and the fence and the building are 6 feet apart. And we have this angle here that is made with the ground and the ladder. Now, we want to find the length of the shortest ladder that will reach from the ground over the fence to the wall of the building. So the first thing we need to do in this example, it gives us a hint to split the ladder into two parts. So that was a big hint. And we need to write the length of the ladder in terms of theta. So I split up the ladder into two pieces. This piece here, I'm labeling it as L1, and then this piece here is L2. So the total length of the ladder is going to be L1 plus L2. Now, using some general trig, I found that the cosine of theta, which is going to be adjacent over hypotenuse, is x1 over L1. And then I solved this for x because I discovered later this is going to be useful for a substitution. So I solved this by doing some cross multiplication for x. Then I also found by using sine of theta, which is opposite over hypotenuse, I have that sine of theta is 30 over L1. And since we need to know what L1 is to make up this equation, the first part of the equation, we need to know what L1 is. When I cross multiplied, I found that L1 is 30 over sine theta. Now, I could have found L1 from this first equation here, but the problem is that we need to find it in terms of theta, according to what the question is asking us to do. And if I use this equation here, I'll have x's and thetas in there, and we don't want that. So I don't want to use this first equation that I found with cosine for L1. But this L1 here is only in terms of theta. So this is what I'm going to use for L1. L2, however, is a little bit more tricky. I had to goof around with it a little bit. To find L2, we're going to use similar triangles. So we have two triangles here. We have the big triangle, which I'm highlighting right now in green. And then we have, let's use blue here. And then we have this small triangle that I'm highlighting in blue. And since they share this same angle here, theta, they're going to be similar triangles. So what I did was I said L1 plus L2, so this is the whole entire hypotenuse of the big triangle, and that's over the hypotenuse of the smaller triangle, which is L1. Then I created another ratio. We have x plus 6, that's the whole side of the big triangle, over x, which is the side of the smaller triangle. And then after doing some manipulation, I found that I could get another ratio, which is L2 over L1, which is equal to 6 over x. Now, I did that by splitting up these two bigger fractions into smaller fractions. So this fraction right here, I split it up into L1 over L1 plus L2 over L1. And then the L1 over L1 became 1, and then I'm left with just L2 over L1. Then I did the same thing with this fraction. I split it up into two separate fractions. I took x over x plus 6 over x, and then the x over x turned into 1, and I'm left with 6 over x. And then by just subtracting 1 from both sides, I'm left with L2 over L1 is equal to 6 over x. Then this is where this substitution came in handy up here. X is equal to L1 times cosine theta. I substituted that in here. And so that gave me L2 is equal to 6 L1 over x. And then here's where I made the substitution. 6 L1 over L1 cosine theta is equal to, and then I could cross off the two L1s, and so L2 becomes 6 over cosine theta. So I got my L2 in terms of theta now, which is 6 over cosine theta. So I got my L1 up here, which is 30 over sine theta, and I got my L2, which is 6 over cosine theta. And for the purposes of taking the derivative, I rewrote it so that it's not a fraction and I don't have to worry about the quotient rule. So I rewrote L1, instead of writing it as 30 over sine x, I wrote it as 30 cosecant x. So this is my L1. And then L2 was 6 over cosine theta, which I rewrote as 6 secant theta, just to make it easier. In my opinion, I think that would be easier to take the derivative. And so when I took the derivative of our ladder function, I got negative 30 cosecant cotangent plus 6 secant tangent x. And now to find the minimum value, I have to set this equal to 0 and solve for x. Actually, I just noticed something, just to be aware of this. I switched from using thetas to x's by accident. All these x's should be thetas, so just be aware of that. So then I set the derivative equal to 0, and I solved for x. Now I had to do a little goofing around to figure out how to solve for x, but you can follow my steps here. I added 30 cosecant x cotangent to both sides, and then I rewrote everything in terms of sine and cosine, and then I cross multiplied, and then I rewrote this. I kept the 5 on the left, and I divided both sides by cosine cubed, and I got 5 is equal to tangent cubed. And then I took the cube root of both sides and then used inverse tangent to get the value of x where we would have the minimum value. Now you should verify that this is a minimum value by making sure that it's on an interval that's concave up. So that's something that wasn't asked of you in the question, but it's definitely something you should check into. And then once you verify that that is actually a minimum value, then you go back and plug that value of x back into your ladder function up here. Let's see, let me use a different color. Up here, here's your ladder function. So take that value of x to find the length of the ladder that would be minimized. So once you do that, when I used this x and I plugged it into that function, I got that the ladder was 47.03592. Now the question specifically asked to round out to 5 places, so I made sure to do that. So you make sure to do that too with your values. But just to sum up real quick, this took a lot of manipulation and a lot of algebra and a lot of trig. There may be an easier way to do it, but this is when I worked through it, this is what I found. And then just remember, when I wrote this out, I accidentally switched from using thetas to x's, so just be aware of that. Hopefully this helps.